Okay. So, hello everyone. Happy Tuesday. We are very glad to welcome you to another installment of the Paleo Perk seminar. And today we are joined by Peter Neff from the University of Minnesota, USA. And today, Peter will be talking to us about accomplishing my grad school dream project, new ice cores from West Antarctic ice rises at the epicenter of ice sheet change. So, for those of you who are new to a Paleo Perk seminar or haven't been here for a long time, we'll go over the format. So, welcome and announcements that's happening right now, followed by the talk, which will be for 30 minutes, and then followed by moderated question answer session. Today, our questions Paleo Perks host is Isaiah. So, don't forget to send your questions via chat to the questions at Paleo Perks host. And then Peter has agreed very kindly to stay with us for an informal tea time. So graduate students, postgraduate students are all welcome to have come talk with Peter in a more relaxed setting. A bit of housekeeping before we get into today's talk. Paleo Perks values the participation of all folks interested in the paleo sciences. Please remember to abide by our code of conduct during today's seminar. Please mute yourself for the duration of the talk out of respect to our speaker. You shouldn't be able to unmute yourself, but in case you do, please mute yourself. You can ask questions by chatting to the questions at Paleo Perks host or by using the raise hand function. If you face any technical issues in the Zoom, please do not hesitate to reach out to the questions at Paleo Perks host. We have closed captions built into Zoom. Use the CC button to show or hide them. Paleo Perks runs in the on the shoulders of outstanding ECR work. So if you know an outstanding early career researcher, please nominate them. The link to the form will be dropped shortly into the chat. We also collect anonymous weekly feedback to assess the demographic of our audience. This form is anonymous and optional, but you're highly encouraged to also respond to this form. The link to the form will be dropped into the chat. Okay, now on to introducing our speaker for today. Peter Neff did his bachelor's and master's at University of Washington in USA, followed by a PhD at Victoria University of Wellington in New Zealand. And currently, Peter is an assistant professor at the University of Minnesota, USA. Peter, please begin your talk.
Great, thank you so much. I'll just share my screen and I'll see if I've messed anything up about how I've shared it. Um, does that look good?
Yep, good.
Great. I last minute had messed up my settings, but well, thank you so much for having me. I've started my timer, so I'll do my best to not go past 30 minutes. Um, yeah, I'm really excited to talk to this group, early career researchers. I feel like I've sort of just emerged from having that title, maybe being 10 years from my PhD in the next month or two. But yeah, I wanted to try to give you a little bit of a sense of this dream project, which just a year and a half ago or so we accomplished, recovering an ice core at a really difficult to reach but critical part of West Antarctica. So I have a bit of a preamble that's sort of about that, finding this obsessive project that's motivated me in the first part of my career. And then I want to give you sort of the science pitch for this main line of research that I'm pursuing in ice core science in Antarctica. And then show you what we did, a little bit, a lot of photos of the field work. I have very few graphs in here, maybe a lot of maps and diagrams of how we think about West Antarctica and the challenges there of ice loss. So yeah, I've been obsessed over the last decade, let's say, with these features, which are called ice rises, and they're features particularly in Antarctica only, and they're grounded regions of ice that's accumulated over millennia from local snowfall, and they have a lot of the conditions that we like for ice core paleoclimate drilling sites. So we've drilled out quite a few Antarctic ice rises over the last few decades, and I've pushed this out with the support of my colleagues at the Korea Polar Research Institute. Um, Pushed us out to a really remote coast of West Antarctica in the Amundsen Sea region, where we're seeing really rapid and globally consequential change in ice flow and increased ice loss contributing to sea level rise. So I must acknowledge my main partner in crime on this project is Young-Chol Han, who's the leader of the Ice Core program at the Korea Polar Research Institute in South Korea. My participation in this project was funded by the National Science Foundation, and the lion's share of the logistical and continued funding for the projects comes from South Korea, the Korea Polar Research Institute. Um, if you don't know ice core scientists, I am one happy to answer any ice core scientist questions, but we like ice domes to put it the most simply. This is a classic diagram from a 1969 paper by our Danish colleagues, Willy Dansgaard and Sigfus Johnson, of the basics of how we think of an ice sheet, an ice divide. Think of it as this nice little lump of ice. This diagram has flow lines where you're flowing from a central stack of accumulating ice. That central location at the ice divide, we call it, is really where you want to be drilling ice cores, where the ice flow is the lowest and the flow geometry is the simplest, where your layers are just being stretched by flow out in the horizontal, and they're also being thinned as they're stretched and compressed from above by each subsequent layer of snow accumulating. In Antarctica, we're lucky to have these additional mini ice domes. They're at the left ringing the edge of Antarctica. And as we see change sort of emanating from coastal regions in Antarctica, they've become more critical, I would argue, as sites to extract paleoclimate information that's going to be helpful in thinking about coastal change in Antarctica. So these coastal ice rises, or we sometimes call them ice domes. I might use that interchangeably. So that's my main focus is these domes on the side of the ice sheet. Right, and that central stack is where we want to be drilling. There's a similar central stack of ice at the ice divide of any smaller ice dome around Antarctica. But you'll see if you look at the map of where we've drilled deep ice cores in Antarctica, we've drilled a lot more ice cores that are really shallow for, spanning decades to centuries across Antarctica. These are the big, deep ones, sometimes many thousands, 2,000, 3,000 meters deep to bedrock. But you'll notice that these are, for the most part, biased inland, where your deep, simple ice flow case at ice divides is located. But there are dots around the edge there at Law Dome on the right, our Australian colleagues in the Ross Sea, sort of bottom center, where the US back in the year 2000 or so drilled at Saiple Dome. Um, and other sites around the periphery, but in general, not a lot of deep ice cores out there. Um, and my thinking about these new locations began when I was working on my PhD based at the Victoria University of Wellington in New Zealand, but putting in a long field season at Roosevelt Island when um, the New Zealanders were leading their first and only so far deep ice core project there. So Roosevelt Island is a nice place to go to if you're new to ice rises because it is the sort of canonical classic ice dome, and it's where a lot of U.S. glaciology research began. This is where Little America stations from Richard Byrd to the early days of the U.S. Antarctic program were located. Um, and if you look at a cross section from radar imagery, it's from our colleague Howard Conway, you see what we like about ice domes and about Antarctic ice rises. You have the dome structure, nice simple stratigraphy you can see there in the radar image. Under the central divide, you have all of those layers that are just being stretched and thinned. They don't have a very complex ice flow. And then we also see this arching of the layers of the isochrones underneath the ice divide. That's called a Raymond arch, named after another professor of mine who did the math on how that ice flow happens underneath the ice divide back in the early 80s, and it actually wasn't observed until right around this radar image came out. And sure enough, you have this upwarping of isochrones beneath an ice divide because that stack of ice is actually slightly stiffer than the ice in different ice flow states. So this is what we want to see at an ice core site. Any Antarctic ice rise essentially has these same features. So we were drilling here in 2012, 2013 season. This is what that operation looked like, drilling at 760 meters or so to bedrock. quite a lot of work, 2 seasons of drilling, much more consequential than the work that we did, just going in very quickly to collect as deep of an ice core as we could in 2 weeks. Um, so this project was 2 seasons of, say, 3 months of work in each of those seasons, plus additional seasons to fly in and fly out all of the equipment that you see here. Um, I suppose I'm probably making a lot of assumptions that a group of paleo folks know the gist of what we do with ice cores, but right in Antarctica we have um, annually resolved chemistry in the snow and ice in ice cores that we can use to annually date ice cores going back tens of thousands of years. And then we use all of that chemistry as environmental proxies, of course. We also have the unique advantage in Antarctica of very clean ice that captures air bubbles that contain samples of the past atmosphere that are almost entirely unaltered and preserve things, including carbon dioxide, which is not preserved anywhere else on the planet besides in Antarctic ice. So as we were out at this site, we started to have conversations, actually, including with Howard Conway there, who provided the first radar images of the stratigraphy at Roosevelt Island, about all the other ice rises in the region. So we were there at Roosevelt Island at the bottom, and out to the east of Roosevelt Island is a totally um, relatively unstudied coastline and increasingly critical coastline for Antarctic change. I'll show you going forward. And so that conversation really is what initiated this obsession of mine that was pretty quickly fed by diving into the archive that is the NASA Operation Icebridge data set. So for a decade from 2009 to 2019, NASA flew extensive airborne missions over the polar ice sheets with high frequency and also deep penetrating radar. And so each of these images is at the summit, that central ice divide uh, of an ice rise around the West Antarctic coast. And ever since seeing this, I've sort of been nattering about the need to extract the information that, if you're a paleoclimate scientist, you see the layers beneath the surface there, whether you study mud or tree rings or ice layers. Those are layers of time. Those are layers of information about the recent past of coastal Antarctica. And if we're worried about coastal Antarctica, we should go and get those layers in an ice core. Um, so, spoiler alert, we did do that at one location so far, and we collected as much ice as deep as we could in the sort of rapid mode of logistics that we had at our disposal. This icebreaker with helicopters, the RV Iran, South Korea's primary Antarctic asset. Um, So ever since getting obsessed with this, I started that more formal process of like, okay, well, how do I will this into the world? As a PhD student transitioning into being a postdoc and seeking a faculty position. What are your tools for getting word out about something like this? I suppose it's talking to colleagues, giving presentations, getting things on paper, and starting to propose the work. So since about the year 2014, I've been doing that. And I think I'm probably best known for nattering on about West Antarctic ice rises more than anything else. This was some slides from the first presentation at sort of an ice core workshop, planning workshop for the US community back during my PhD, 2014. It wasn't until about 2020 that a colleague, Amelia Chevenel, invited me to write up just a little two-pager, not really peer-reviewed article about the opportunity in the journal Oceanography, thinking that folks with icebreakers with research vessels read journals like Oceanography. And sure enough, they do, because about 2 years later, my colleague Young Chol in South Korea emailed me asking about how things were going with this concept. And I responded, well, not well. We haven't really done anything, but uh, a few conversations and planning meetings later, he was able to really motivate within the Korea Polar Research Institute the support for this project. And so again, we must credit Young Chol for then 4 years later getting us to this point. Two different drilling teams, U.S. and Korean drilling teams, drilling just a kilometer apart at this site, Canisteo Peninsula, that I'll take you to in a little bit. Um, both teams successfully drilled 150-meter deep ice cores, which I don't know if that sounds like a lot, depending on your paleo perspective, or a little if you work with deeper ice cores. But 150 meters is about as deep as you can get before you really need to upgrade to a heavier mode of drill infrastructure for Antarctic ice core drilling because of the pressures you're reaching when you drill that deep. So we were really hard out to get that number 150, and both teams did. And I'll show you how we did that. But first, I'll spend, so let's see, we're just over 10 minutes in here. I'll spend hopefully maybe another 10 minutes giving you the science background before wrapping up with maybe 10 minutes about just exactly how we got these cores. Um, so scientifically, my motivation certainly in Antarctica is it sort of relates to this. The title of this paper, which is now from 2 years ago, say, the quandary of detecting the signature of climate change in Antarctica. So in Antarctica, our observations of climate, of weather, only extend at best, let's say back to 1957 to the International Geophysical Year, where most permanent research stations and weather observations began. And we know that climate in Antarctica is some of the most variable on a year-to-year basis of anywhere on the planet. Um, and we also are not seeing rapid emergence of human-caused warming like we are in the Arctic, because the processes and the Antarctic system is quite different than the Arctic system, where you have rapidly changing things like Arctic sea ice that are leading to feedbacks that feed into the rapid increases in temperature that are observed there. So Antarctica is always limited in observations, both in space, where we have those observations, and in time, when and how long we have those observations. So ice cores are really good for that in a snowy, cold place. You can go anywhere and drill an ice core and gain that past perspective. So long as it has the right flow condition, then it's a good drilling site. So the kicker of this paper, this is a stack of water isotope records, a temperature proxy for Antarctica. You see a lot of noise over that last 1,000 years. You don't see a super strong temperature anomaly, but this work by Mathieu Casado and others showed that the climate models underestimate the impact of polar amplification in Antarctica as well as the Arctic. And they underestimated both in the natural variability and the magnitude of the anthropogenic warming that should be observed. And so essentially, if you're underestimating by a factor of two the warming that is actually happening in Antarctica, you're missing having that input into things like ice sheet models and models that are producing projections of sea level rise. So we want to understand Antarctic climate as best as possible. I think you all can relate to that as paleoclimate scientists who I assume are similarly trying to fill in gaps in space and time in our understanding of Earth systems. So yeah, I'm an ice core scientist, so of course I I say that the way to, oh, I'm sorry, I highlighted here another niggling problem for us that I've been harping on over the years is you see that this plot of the number of records over this sequence is maximum over the last 200 years. That's certainly accurate. Our perspective on Antarctic climate is most complete for the last 200 years, but it is the most incomplete in the last 20 years because we've been very successful at collecting cores all across Antarctica say in the 1990s and 2000s, 2010s. And we don't go back to those locations to do the shallow coring, connecting them to present day so that we would have the same number of records extending to the year 2020 or 2025. So we actually have a problem where we need to go back to all of our Antarctic ice core sites to update that so that we have continuous perspective, especially if we expect a climate signal, human-caused warming signal to be emerging in Antarctica. So I'm an ice core scientist. My solution to this is that we need everything everywhere all at once, or ice cores everywhere all at once. So we're trying to get out to all those places and do that and fill in gaps in space and in time in Antarctica. So we certainly have gotten out to a region where we are really undersampled in space in West Antarctica. So I'll take you through as much as I can of that in the next bit of the presentation here. So now we're going to Antarctica. I've put on the map 3 red dots that are essentially our logistical hubs for the U.S. Antarctic research, McMurdo Station, which in general supports our deep field science and also supports South Pole Station. Palmer's out there on the Antarctic Peninsula doesn't support ice core research, but other important research. If we add on all the other international Antarctic research stations, you can see that unlike the deep ice cores we have, research stations are biased towards the coast, except for the few permanent inland stations, South Pole, Vostok, Dome C. But there's a conspicuous gap here, right, where we are not biased towards the coast in our presence. Research stations are where we have modern climate records. We don't have that in West Antarctica. It's sort of a quirk of geography. This is at the southern end of the Pacific Ocean. Most of the moisture and storms that enter Antarctica actually enter through West Antarctica. So the coastline there is not a great place to be. There was a Russian research station out there in the 1980s, but that closed with the fall of the Soviet Union. And just to show you how big of a place this is, we slapped the United States on there roughly to scale. So this coastline is the equivalent of the west coast of the U.S., not having any cities on it, not having any weather and climate observations. There are scattered automated weather stations out there, but there aren't ice cores by and large along that coastline of any length of time. So this has been again my driving motivation in my career. And so let's see, we can add some more color onto this map if we put on some satellite observations of change in Antarctica. And we'll see that this is not just some random part of Antarctica that we just need to fill in. It's actually the place where there's the most red in the thinning of the Antarctic ice sheet as seen by IceSat and IceSat-2. These are laser altimeter satellites that NASA has IceSat-2 up in orbit still. Um, very simply, red is bad, blue is good. If you're an ice sheet, if you care about ice flowing into the ocean and raising sea level, and by and large, the region of persistent, widespread thinning ice that's in imbalance, it's lowering the surface of the ice sheet because it's not in balance. West Antarctica, coastal West Antarctica is where that is happening. There are a few other hot spots that we're looking into as a research community, but it's generally agreed, and multiple data sets show this, that the ice loss from coastal West Antarctica has been persistent and in a lot of cases accelerating over the satellite observational period, right? Which really doesn't begin until really is say year 2000 to present for satellites that have detectors like laser altimeters or radar altimeters or gravity measurements, right? The GRACE satellites also show that this region is very unique in just how widespread and persistent ice loss is. So great spot to gain some more climate perspective, really bad spot to not have long-term climate perspective. So I mean, the arguments here are pretty simple, and I'll try not to spend too much more time on it because I can already see that I'm going longer than I wanted to. So if you haven't heard of Thwaites Glacier, that's sort of the main, most concerning unstable glacier out here. It's sort of in a bad geometry where if it starts or continues to retreat, it could be in a runaway retreat that could contribute multiple feet to sea level rise. And we, as an Antarctic research community, want to understand how much of that sea level rise is going to come from West Antarctica and how fast. So we're all trying to bring our different resources to bear on that. But essentially, all aspects of the system are in play. The ice is changing, forced by the ocean. The ocean is changing, forced by the atmosphere, by winds that are upwelling relatively warm water bodies underneath floating ice shelves, the floating extension of glaciers in Antarctica. And actually, the solid earth beneath is responding to unloading of that ice and it can be actually mitigating some of the loss that would happen if that crust weren't responding so quickly. So ice cores can't bear on all of these different factors, but they certainly can on quite a few. And this has been my argument to get us out there. Drilling 150-meter deep ice core. Unfortunately, this is a really, really snowy part of Antarctica. 150 meters is really going to get you 100 to 150 years of time because it's that snowy out there, 1 meter per year of snow accumulation or more. So you got to get out there and you got to drill deep cores to get any time perspective. But those cores are going to give us perspective on sort of the global atmospheric factors affecting the region, local snow accumulation, local synoptic climate features, weather and climate features like the Amundsen Sea low is like sort of the equivalent to the Aleutian low if you have a North American perspective like I do. Um, so we're trying to add ice cores to all of the different tools we have to understand changing glaciers in West Antarctica. Okay, so back to the map. And um, there's a gap here, which also implies it's not the easiest place to get to if you're starting to think about how do we get an ice core there and get it back to a research station to then ship back to labs in the United States or another country. And if you look at the map of all of our airfields in Antarctica, indeed, that coastline of West Antarctica is the only one that's not reachable from a runway by the sort of smallest, most versatile aircraft we have in Antarctica, the Twin Otter. So you got to be creative in getting out there. Either you're putting together really long fixed wing aircraft chains, or uh, or you got to go another way, say an icebreaker and helicopters, which really has not been done for ice core projects in Antarctica. Um, So again, we don't have research stations out there, but I've already introduced you to ice rises. And if we put them on the map, you'll see that they are the locations that we have the opportunity to go um, and fill in those gaps by collecting ice cores. So I might skip through a couple of slides here just for time. Our overview of ice rises, another sort of diagram there. But again, they have all of the ice flow conditions we like for ice coring. They are in the complexity of the coastal region, which in the past has been bad. That sort of wasn't the driving question. Wanting big, broad Antarctic-wide or globally relevant greenhouse gas records. That's what's kept our ice core drilling to inland regions. But if you're thinking about change in West Antarctica, ice rises are right there in the mix of all of the processes that matter. So we like that they're there in that complexity. Just one more sort of overview diagram. This is a cross section through the ice sheet from bed map 2, and you can again see just how different we are in the coastal ice rise position there from our inland cores. And if we're worried about, so we say ice ocean atmosphere interactions are sort of the important triple point of interactions that are driving ice loss in West Antarctica. These ice rises are pretty ideally located for getting at that. So we'll put on the previous ice rises that have been cored to bedrock on these locations. I guess not all of these that I have mapped went to bedrock. I have an open circle out there actually in West Antarctica where a rapid access borehole was drilled a couple years ago by the British Antarctic Survey, but that didn't provide a full climate record. It only provided some information about how old the ice got with depth. They were sort of pursuing a different research question, trying to see what the oldest ice preserved at these ice rises is, rather than collect records of the last 100 or 200 years to improve our understanding of recent climate. So we added a star to this map, relatively close to that British Antarctic Survey location in the Amundsen Sea, but we're going to be providing the first year-to-year records of climate and environmental variability over the last 100 years. And I'll show you a little bit of that data by the end, the only data that I have in here, so long as I can generally stick to time. And I know I'm in my last 7 or 8 minutes here already. So let's go down there. So if we zoom in on the region, I think, let's see, this is just a multi-year time series of how the sea ice moves in this location. I'll add the cast of characters. We have two ice rises that I have circled there. The one on the left, Martin Peninsula MP, was actually our target for this expedition to Antarctica that Young Chul and I managed to get together with the Korean icebreaker. Unfortunately, we were pushed to Canisteo Peninsula as our drill site due to the sea ice conditions there. You can sort of see that sea ice gets um, stuck and supported in the middle of the Amundsen Sea, which logistically separates the western and eastern regions. And so we had to make the decision to, after arriving in the Amundsen Sea, so a 10-day sail from New Zealand, that the sea ice conditions made it too dangerous to leave us at Martin Peninsula and the ship to then go on and do the science it needed to in Pine Island Bay. So we needed to stay closer to them. Canisteo Peninsula kept us within less than a day response time for the ship to respond to any emergency for us. And the ship then also could do science while we were off the ship for our what turned out to be just about 2 weeks of drilling. This is what Canisteo Peninsula looked like as we were approaching it. So again, your site is right there at the triple point where the atmosphere, the ice, and the ocean are all interacting. Great place to have a paleoclimate record if those variables are at play in forcing change in the region. Um, so again, it's very rare to have ice core collected by helicopter and icebreakers in Antarctica. We are actually, to our knowledge, is the only project that has entirely collected an ice core without any other logistical support except for that emanating from the icebreaker. So we didn't really think that this was going to work. We didn't know how much time we'd have off the ship, but it turns out that everything aligned. We got our full 7,000 kilos of camp equipment and people, 8 people off the ship, and 13 days later managed to get everything back from the site to the ship, including the additional 5,000 kilos or so of ice that 300 meters of core represents. And each time we put in camp and took out camp, that's something like a dozen or 12 to 17 flights with these two light helicopters that are on board the ship. And it's pretty time effective for the ship to spent 36 hours in position trying to get us off the ship, getting the weather windows we needed to be off the ship, and then was able to go do other science for the 13 days that we did our work, and only needed another, say, 24 hours to pull us back. So 2 days of time on the ship dedicated to support 2 weeks of science accomplishments. When you're running a Antarctic cruise, time is of the essence to balance all of the different science priorities of all the different teams that are on a research vessel. Um, so a little bit here of what it looked like, and I'll try to wrap up and get on to questions. I certainly have extra slides if things come up with questions. So we took one day to start trying to get into camp, but in Antarctica, a primary hazard for flying is when you have high cloud over snow. It makes for really, really bad ground reference for the pilots. It's very dangerous. Probably most of the helicopter incidents in Antarctica have been due to that loss of ground reference. So we got one load in that day, but then had to pull back to the ship, and we were pretty depressed. Things didn't look good. The weather forecast didn't look good for the next day, but the expedition leader and ship captain were going to give us the next morning to see what the weather did before having to go on to do other science and potentially cut our time for science in half. So we were pretty bummed out. Went to bed worried because we were losing our weather window before a big storm was coming, and we wanted sort of counterintuitively, we wanted to get off the ship, even if a storm was coming, because you can spend the time weathering a storm when you're off the ship, and then as soon as it stops being stormy conditions, you can get on with your work, rather than wait for weather conditions to be perfect for flying after a storm. So we weren't feeling the most optimistic when we woke up the next day, but it turned out to be, it doesn't look like it in these images, but it was a bluebird morning. We used the entirety of this 4 hour weather window. These pictures again are near the end of the weather window as it was starting to cloud up again. Used that whole weather window, luckily, to get off the ship. Um, and prepare for that storm, which then was the next occupied our next 36 hours. There are videos of this online if you want to see what it really was like. We lost some tents, but thankfully things just were broken and buried. They weren't blown away, so we didn't lose any equipment, and we sort of quickly just regained ground. We actually continued using this big tent that got crushed for the entire time. We were pretty proud of it by the end. I think I have a picture at the end here. And as soon as that storm was over, we were able to start unpacking, getting drills set up. So this is the sort of heft of what a drill looks like that you need to collect a 150-meter deep ice core. Any ice core before you need to upgrade to drilling with drill fluid. When we drill below about 200 meters, that's where the ice pressure gets great enough that cores start fracturing without a drilling fluid, and that just gets your logistics much more complicated very quickly. Um, so our ice core drilling in the United States is supported by the National Science Foundation Ice Drilling Program, which is an awesome group of engineers who have equipment and drilling expertise. They're based at the University of Wisconsin, actually just a couple 4 or 5 hour drive from where I am. Um, yeah, very simple operation. And as soon as you get it set up, you just drill, drill, drill. And usually our field seasons are sort of marathons in Antarctica, just sort of slow, steady, plodding progress, multiple weeks to get to a place, multiple weeks on site to drill a core. And this was my first project that was an absolute sprint. Get out, take your time on the ship. The whole expedition was 60 days, but once we got off the ship, we knew we had no more than 2 weeks to drill, drill, drill as much as we could. And we can only drill something like 20 or 30 meters a day. So time was a factor. So all we did was drill, eat, and sleep. But actually, we had plenty of time for eating and sleeping. We just um, didn't do anything else besides eat, drill, and sleep. The Korean drill setup was much smaller than ours. They had a new drill system and they didn't have a tent that could shelter it. So thankfully, we didn't have any other considerable storms after the initial one. Um, and their drilling went relatively well also once the storms were over. And it's really unique. Usually we're in these interior sites drilling ice cores in Antarctica. So this picture in the bottom, you can see in the distance there, not far from Etienne, who's walking there. You can see icebergs out in the Amundsen Sea and Bayman in the distance there, which again, hits home how connected these locations are, being just 10 kilometers from the open water and all of these processes that we need to understand the future of the Antarctic ice sheet. So very rapid ice core drilling, 13 days on site, just 7 days of drilling to get our two essentially identical 150-meter deep cores. This is our drilling progress. Essentially, once each team's drill was set up, we just plowed our way down to our 150-meter target, with only the typical sort of issues we have in the field. So I'll just keep going because I'm already at 31 minutes here. So this is a high resolution radar image of the top 80 meters of the snowpack at the site that Vikram Goel is a geophysics a glacial geophysics expert in India, and he was driving around skidoos with radar, collected about 300 kilometers of this surface high resolution radar to look at the variability in the snow accumulation. So the depth of any layer there, those are isochrones, layers of continual time. Their exact depth is controlled by the snow accumulation at that one point location. And you can see the two different drill locations. US, we drilled 500 meters on one side of the ice divide. The Koreans drilled 500 meters on the other. We camped in the middle, so we could just walk out to our drill sites. We drilled at a relative low in accumulation, so we should have maybe an extra decade in our record as far as time. And the Koreans drilled in the local accumulation high. Um, if you look deeper, we actually were the second team to get full deep radar out there to get ice thickness. Actually, this is a new observation of Antarctic ice thickness that we need to get out into our big continent-wide data sets. So it's 650 meters thick, and you can see again one of those things we like to see at ice core sites, that arching of the layers beneath the divide. It's actually a very mature arch. This suggests that the site's been stable. To get that arching to happen and to be a double arch takes something like 10 times the response time of that site. The response time here is it's proportional to the snow accumulation and the ice thickness. Uh, all to say, the site's probably been stable. The divide has been at that same location probably for the last 4,000 years at least to form that feature. Okay, we'll be pulling out now and I'll be wrapping up. So this is what pull out looks like. I know that videos sometimes don't look great on Zoom, so if this is a little glitchy, I apologize. And then I have a few more photos and I'll wrap up and we can chat. So again, these helicopters are essential tools to do any glaciology or oceanography projects in coastal Antarctica, because there's this crevassed region at the edge of the continent, at the edge of any glacier system, that you can't get through with smaller boats. You have to get over it uh, with helicopters, unless you bring say an aircraft carrier, which actually has been done in Antarctica, but only back in the 1940s in the very first U.S. Navy expeditions to Antarctica. Um, so as you know, as soon as we were done drilling, we maybe had one day to tidy things up, and then we started packing our equipment away before the helicopters arrived, and I was coordinating all of our aviation to then grab our ice cores and get them back to the ship, get them over that crevassed region, which again is why helicopters are absolutely essential for coastal Antarctic glaciology. And I harp on this point because it's something that we have not had the capacity to do in the U.S. Antarctic program, and we won't going forward based on our research vessels that we currently have, that we are not going to have soon, and the future vessels that being designed right now that don't have helicopter capability. So just the sort of final how we get projects done. Ice has to go in a freezer and then get all the way back to labs. The Aeron has two freezers that can just fit 150 meters of core each. We put one core in each freezer, so we had redundancy if any freezers failed. So I could not be a bigger fan of the South Korean icebreaker, Iran, and my colleagues in South Korea. So I've been trying to cheer them on as much as possible. They are leading the world in their ambitious multidisciplinary tasking of this ship, especially the use of helicopters for coastal Antarctic glaciology and oceanography. We don't have that in the United States. The Nathaniel B. Palmer can have helicopters, but historically has not. And that vessel is being handed back to its owner in a matter of months now, due to tight budgets and budget uncertainty in the U.S. So the Koreans are going to continue to lead. Other countries like the British Antarctic Survey and Germany, South Africa have ships similar to this, but nobody's been tasking it like South Korea has. So um, these projects don't get done without a whole lot of people, and Young Chol is really the person who should be out talking about this project. He's very busy keeping his research program going and actually working on sampling the cores, which they have been done. So the last thing I'll show here are the preliminary data from the core that the Koreans drilled. So our U.S. drilled core is actually still in the freezer in South Korea, and we hope to analyze it in the next year. Their core is very high snow accumulation, 1.5 meters per year, which from a time perspective, how much time you have preserved is not great. I won't step through all of this, but this is just showing by depth in the core, the density, actual measurements of methane. So our colleagues in Korea, Jinho An and his master student Hyung-hee Lee measured methane in the Korean core, which is actually really well preserved despite the relatively warm site. This is now the youngest, highest resolution greenhouse gas record anywhere in Antarctica. We'll be measuring more of that going forward. they got the first estimates on the accumulation rate from this modeling here, and also the age of the ice, which um, the ice is older than the air trapped within it, but the ice at the bottom of the Korean core seems to go back to the year 1920. So we're going to have right around a 100-year record of climate in the region. Um, Again, I think I've highlighted that there are a lot of opportunities around the coast here. We've ticked one box for getting the first century perspective in the Amundsen Sea, but there are other sites out there that could help us constrain some of the other variables that are at play in the climate system of coastal West Antarctica. Um, so the last thing that I'll say, I'll show this team that succeeded despite the ugly home behind us, and then remind you, thinking of what's driving your passion in grad school right now. Unfortunately, projects, particularly in Antarctica, and I know you're not all Antarctic scientists by any mean, you have to be thinking, about the long game in addition to whatever project is in front of you that you're doing for your supervisor, or you might be doing for your postdoctoral advisor. So for right now, I guess we've already ticked over another year here. So what project you want to do in 2035, you need to be thinking about right now. And so I got really lucky along the way for this to have come to be, and I hope it's not the last big project, but certainly we're now in the lucky position of having cores and having paleoclimate records to develop from them. So if you want to see more of what this looked like, I recently posted like 80 minutes of my high resolution video that I managed to take along the way here. I do share a fair amount on social media, although less in the last year. It's sort of burnt out, but need to get back on it. So thank you guys very much for having me. And I did go a little bit longer than I wanted to. So let's make sure we take time for question and answers. And I certainly will be here for the full tea time if you'd like. So thank you very much. I'll leave my slides up here in case folks have questions that are relevant to them. And yeah,
Thank you, Peter. This was a very exciting talk, and all your videos and photographs really put things into context. I would like our audience seems to have really enjoyed your talk as well. I would like to remind everyone that if you have any questions, now is the time to put them in the chat for everyone to read, or you can send it to our questions host if you want to ask an anonymous question, or you can just raise your hand to talk to Peter. So we have a first question here by Alexis. At such low altitude coastal sites, are summer melt events possible?
yeah, great question. And they absolutely are. We did see, just as we were logging the cores and they're going by right when you're in the field, all we do with our ice cores are essentially bag them and tag them. But we did see melt layers going by. This is a site where we took the temperature of the cores as we were packaging them up to, and the temperatures were around -11, -12 degrees Celsius. Which does mean that in the summertime, some years in the most anomalous events, you can get slightly above freezing. That can be a concern at places. I mean, it's a concern for the ice shelves around these locations, which are 500 meters lower in elevation and get quite wet in the summertime. That's a big process that we're thinking about in a warmer Antarctica. Melt layers and ice cores, though, it can be one of the most direct signatures of temperature. Temperatures above zero make melt layers at cold sites. So other places, other coastal Antarctic ice cores, like the James Ross Island core on the northern tip of the Antarctic Peninsula, actually one of the only other ice cores that was collected in part by with helicopter and ship support. The record of melt layers there that was published probably more than a decade ago now by Nerily Abram in Australia. Um, that melt layer record shows an increase in the frequency of melt events in the 20th century, which again is one of the most direct indicators of temperature and a direct indicator of change. That in the Antarctic Peninsula is clearer than any other part of Antarctica. So yeah, great question. We would hope if we could drill the unlimited number of ice cores in these regions, I would think drilling them at slightly different elevations would be really interesting to see how the numbers of melt layers change with elevation. But of course, our opportunities to collect cores require so much logistical support that we don't get many chances.
We have one raised hand. And so, Sophia, you should be able to ask your question.
Perfect. Hi, thank you so much for this great talk. And my question, I'm curious in some of the atmospheric constraints that you were mentioning, such as the imminency low, if any anthropogenic signal is visible yet, or if the natural variability in these signals is still too great for that signal to emerge.
Yeah, that's a really good question. And that tends to be one of the harder ones in Antarctica because our best observations are especially along a coast. So the Amundsen Sea affects the coast of West Antarctica, where we have no station observations. So we're restricted to the satellite era, where we have satellite observations of clouds, which also feed into some constraints on atmospheric motion since the satellite era. So we have, say, 40, 45 years of data now um, to look at that variability and see if trends are emerging. So there is, in general, a trend towards strengthening westerly winds, which plays into the behavior of the Amundsen Sea low. Um, there's a relatively important fluctuations from El Nino, La Nina in coastal West Antarctica because we're at the southern end of the Pacific Basin. It's one of my other sort of things. Like, remember how big, how flat, how energetic the Pacific Ocean is, and it just so happens that West Antarctica is at the southern end of it. So if there are atmospheric ripples that emanate from really strong El Nino or La Nina events, those do make it down to coastal West Antarctica, which just adds complexity. Again, we're in a place where you have short, noisy climate records. So again, we want to make our climate record not just 45 years, but at least double it. We went through a lot of work to potentially double that length of time in the Amundsen Sea. There are also, what controls snowfall at any ice rise along such a broad coastline also really varies, right? Like, uh, I mean, if we go uh, back to my map here, these other sites, the one we drilled at, that's like having a ice core in coastal, say that, coastal Washington State. And if you go down to the other, towards the Ross Sea, any of these other opportunities, that's like getting down to California or, and how different is coastal Washington State to coastal Southern California, right? They're very different climates. My PhD student, Julia Andreasen, who recently graduated, is finishing up a climate classification for Antarctica to try to get across this point that especially on maps like this that are all gray, it sort of implies that all of Antarctica is relatively the same. But when you're moving across such a huge band of longitude, what I'm getting at is that, the controls on snowfall at one site are specifically the westernmost sites towards the Ross Sea there. The snowfall is really strongly controlled by the strength of the westerly winds, which I mentioned is one of the things that we've seen an anthropogenic signal in. We think in the short data sets that we have. It'd be nice to have longer data sets to confirm. Where we drilled, actually, there's a complex confluence of climate factors that affect the climate right at, say, Thwaites Glacier. So we'll have a site that really, really experiences the climate that Thwaites Glacier does, but it can't tease out just what the westerly winds are doing to affect snowfall in Antarctica. So again, we'd like to have this array, the Ross Amundsen Ice Core array, because then we can best piece together all those different things. But it'll take us to probably 2 decades if we were to really try to chip away at these three other sites. I would hope we can get it at one or two of these other ones, but the opportunities are so slim that the Korean icebreaker goes back to the Amundsen Sea essentially every other year now. But of course, the schedule for one nation's Antarctic research vessel is pretty full. So it's already has its the rest of the decade planned out. So you can't just on a whim, tell a ship to go back down to these locations, I suppose, unless you're not resource limited, but we tend to always be. But I guess I need to befriend a billionaire and then we could make better progress.
Ah, that is, yeah, we have a few comments and questions in the chat, but I'm going to read out this one first. Jack is asking, you took duplicate course, which is difficult slash rare to do in any coring based earth science. So how are you planning to use these duplicate cores? Any different analysis applied to the two cores, or will you be averaging them along isochrones?
Yeah, super good question. And that, we're in the lucky position of just about having the data from the first core. They're sort of in the final process of cleaning up the data after what we call continuous flow analysis campaigns, where we're melting each core half meter by half meter to get our high resolution chemistry data. Um, the Koreans have a really nice facility. I finally was able to visit just this past July. So we can see how those data look, and if there are any issues, redo the same analyses in the subsequent core. We of course want to have a lot of similarities in analyses across the cores because especially because each core is going to be slightly different accumulation. I just from a rough estimate in those radar images, I think our US drilled core is going to have about 10% less snow accumulation. So 10% more time, which is say maybe tack on another decade to the record. So maybe our core will go back to the year 1910. But it should be really good for right being able to identify what is climate signal and what is local depositional noise, right? It's a depositional environment, just like the bottom of a lake or a tree ring in the Great Basin if you're a Harna. And you got to establish what your signal to noise is. And yeah, we don't do that. It's that, in some ways, sort of the devil's on your shoulder or whatever. Oh, let's only collect one core because then we won't know how noisy the signal is. But if you collect two, then you can immediately start to refine a little bit what your signal to noise is, which will be really, really important. And it's just great to have more sample volume at a place where, I think we probably were, so we 8 people in our camp. That probably makes 10 people that have ever been to this location. And the odds of anybody ever going back are quite low. So, getting two cores, our US core is 9.8 centimeter diameter. The Korean core is a little bit narrower. I don't remember exactly. So that also means, we potentially can make two sets of duplicate samples in a core of that size. And we also, right, we need to think about how much ice we need for gas analyses versus chemistry analyses. Um, yeah, so we're really lucky to be in that position. And I think that my Korean colleagues are probably, because our core is in South Korea, I had great designs to ship it here to the States, but it seems very high risk and very expensive. And once I saw their facilities are really world class at Copri, and they've finally built up a really nice ice core lab just for these projects. We're in a good position there. So it was really surprising and gratifying to me as well. My colleague Young Chol, after we collected these cores, uh, emphasized to me that these were the first sort of grassroots science motivated ice cores that Copri had ever collected. And previously, they were developing an ice core program in response to sort of top down initiatives to be increasing the profile of the science they're doing in Antarctica. Um, and it's really in these international partnerships that they're able to bring an idea in and then motivate their logistical and research apparatus to then support those ideas. So again, I can't speak more highly of Young Chol for really being motivated to go well beyond his expectations within the confines of his position to get the equipment and permissions and everything ready to be able to collect an ice core from their ship for the first time.
Oh, thank you for that answer, um, and sharing all the details about the project. So, Jason is asking, you mentioned that the ice rise has probably been stable for 1,000 years. Can you have an ice rise stability through a retreat re-advance event? I believe some of the Cosmo evidence from nearby suggests that retreat re-advance occurred in the ice and stabilized later around 1.4 Ka. So obviously there are slight different sites. But I'm curious your perspective on re-advance in the ASE and if the stability of ice rises can support the timing or if they cannot be reconciled easily. A very long
Yeah,
question.
yeah, no, it's a great question. And certainly, the kind of timing constraints we get from ice rises can factor into those bigger, sort of more geologic timescale and geologic ice flow constraints from cosmogenic and other data sets. So folks that were part of the International Thwaites Glacier collaboration of the last 5 to 10 years have done some of that work. And there was subglacial rock drilling just 50, 80 kilometers from Canisteo Peninsula a year before we were there to try to get at some of these longer term glaciological changes. So yeah, I can't think of what the signal of a retreat and readvance would look like at an ice rise. Um, we probably we're only seeing whatever the most recent stabilization and accumulation of ice is at Canisteo Peninsula. I don't know, what a model would show of how persistent these ice rises could be if, going back, say, to the last interglacial, to the Eemian. They are yeah, sea level would factor into that. But right, these are sitting on bedrock features that don't just go away. So long as you have a source of ice accumulating and building up on them, you're going to have ice rises there for quite a long time. And we see that at other sites. I see Reed Shearer's on the call. He's played around with some of the sediments we recovered from the bottom of Roosevelt Island, where I started with my presentation, and that bottom ice as well is likely more than 80,000 years old, and I think it seems even likely that it could be from the last interglacial period. So these ice rises can be quite persistent, but they are interesting because they interact with these ice streams and ice shelves that are more dynamic, so they can preserve some signature there. I feel like I just talked around that question, but yeah, a classic thing to do is with it once you get radar imagery of an ice rise, you can do ice modeling to try to see what conditions for stability and snow accumulation you need to reproduce those arches that are buried deep in the site.
Thank you. I think we have this is probably going to be our second last question. So we have, and this is so Shrisha is asking what is the idea behind choosing location site as West Antarctica as compared to any central part of Antarctica, and I think there is a similar anonymous question which is asking what is the reason we have more ice core sites inland compared to the coastline, and why are there more stations at the coast than inland?
Yeah. I mean, starting with the stations, we access Antarctica from outside of Antarctica because we are humans and we don't live in Antarctica by and large. So, and everybody's logistics to support life and research in Antarctica emanates from either continents outside of Antarctica or ships coming from the ocean. So that's the coastal bias is just a purely practical thing, and then it becomes very resource intensive to establish and maintain research stations inland. So they're I guess all of them now are mostly supported by tractor trains every summer to resupply fuel and equipment. That's true of South Pole Station. We used to do a lot of flying to South Pole Station, but it's more efficient to drag equipment with tractors. Um, and similarly with our deep ice core sites, big, uh, multi-group national prestige projects of ice cores are looking for the longest records of climate in Antarctica, and so they go inland to the thickest accumulation of ice, where depending on your annual snow accumulation rate, you can be packing in time up to the previous record of the longest continuous ice core is 800,000 years of time from the Epica Dome C, the European Consortium core uh, at the French-Italian station there. That group also just finished drilling the Beyond Epica ice core, which seems like it's going to be producing a continuous 1.2 or even 1.5 million year long ice core, which is sort of the big international a big international target in Antarctica. Um, in West Antarctica, the U.S. community has drilled multiple places inland to try to find deep signatures of the last interglacial to answer the question whether or not West Antarctica collapsed during the Eemian 120, 130,000 years ago, because that's sort of the climate we're heading to with human-caused warming. We haven't found that old ice preserved. So we drilled at, say, Waste Divide in central West Antarctica, that's actually the first project I worked on in Antarctica as a master's student. That's the second deepest core ever drilled, 3,400. Unfortunately, it was not somewhere where they reached ice that was 100,000 years old at the bed. I think the oldest dated ice in that core was 68,000 years. I think that's about right, which is a bummer if you were looking for that old signature of a collapse of the ice sheet. But that makes the Waste Divide ice core the highest resolution record of the last deglaciation that we will ever have. Right? I don't think anybody's ever going to drill a 2 mile deep ice core just for 70,000 years of information again. And the inland, drilling on top of this dome of ice is just the simplest case, and all of your proxies and the way we think about how snow and water stable isotopes are deposited on the ice sheet with a climate signature, everything is simplified and sort of distilled when you're in the high, dry, cold of central Antarctic ice divides. Um, but all of that thinking originated before our understanding of the current problem in West Antarctica, that coastal change and thinning of ice shelves and upstream ice that's forced by the ocean. That concept really emerged post year 2000 and really matured in the 2010s. Our understanding that ice shelf change in Antarctica was driven by basal melt, warm ocean melting the ice shelves from below. Um, and I guess I'm probably the only crazy person that is really, as an ice core scientist who interacts with that sort of glaciological understanding of Antarctica, I think I'm the only ice core scientist perhaps in the world that says, hey, ice core scientists have something to provide to that, what's sort of seen as a glaciology or a satellite observation problem of like what's going on at Thwaites Glacier. Ice cores can't get you. I mean, we could drill an ice core to look at the bed of Thwaites Glacier in a footprint that big, but they're not generally seen as one of like the geophysical tools that are applied to Thwaites Glacier, like as part of the big US UK International Thwaites Glacier collaboration. We actually tried to get ice cores as a part of that, but weren't successful. So now entirely separately, it's just really trying to get us out to, still ice domes, not an interior ice dome, but coastal ice domes that are in every other way great ice core sites. They're just in that much more complex, much noisier coastal climate. And noisier, right? Like if you're 10 kilometers from the ocean, our concentrations of marine salts and things are going to be, like dialed up to 11 compared to at a site that's 500 kilometers from the ocean. Um, that can be a problem. So say like one of our really important tools in ice core dating is sulfur peaks from tropical volcanic eruptions, right? So that you can go back to uh, the year that Tambora happened, the year that Krakatoa happened, and your dating uncertainty goes to zero if you outside of your annual peak. So we have an annual peak in sulfur from how the surface ocean melts every summer in Antarctica. If and that looks like this. If you have a tropical volcanic sulfur peak, it's like very clearly emerges from the background noise of sulfur in the Antarctic environment. But if you're out on the ocean, your sulfur is dialed up to here, so your volcanic peak might barely emerge from that. So that can be a challenge. There are challenges associated with coastal ice core sites, but the main challenge in Antarctic science is how are coastal regions changing and how are they going to be sending sea level rise to all of us going forward. And so ice cores, in my view, need to be a part of that. We all need to be, if there were trees out there, right, you'd want to throw tree rings at it. We got to throw everything we have at these big globally important questions. So I wish it was more than just, this team of crazy goofballs out there collecting ice cores, but I suppose, I haven't quite motivated that level of support yet. So there's always more to do and an infinite number of ice core sites in Antarctica. So hopefully if I give this talk again in 10 years, we'll have another one or two, but you never know.
Uh, this is our last question. Do you see? I think it's quite aligned to what you ended your answer with. Do you see ice core science, the way it's conducted, changing in the years uh, due to changing climate, melting ice, and
Mhm.
I mean even the political situation?
Yeah. Yeah, certainly. In Antarctica, the change is slower to emerge unless you're on the Antarctic Peninsula. But already at other locations, so another ice core site of mine is in British Columbia. We drilled a core 2 summers ago at Mount Waddington in southern British Columbia, the southernmost annually datable ice core in North America. That site's thinned probably. We tried drilling there in 2010 for the first time. Since 2010, it's probably the top of the glacier is thinned by about 5 meters. And we might be starting to lose some of the records that are preserved in a glacier like that. That's certainly the case in the European Alps and other locations in alpine regions. But yeah, I mean, I think we're already into the sort of, I don't know, you could argue about this, like the sort of second or third generation of ice core scientists, folks who did their PhDs with the original folks who started ice core science, so like Willie Dansgaard, who I mentioned at the very beginning. Dorte Dahl Jensen is still leading the ice core team in Denmark. She did her PhD with Willie, and there are colleagues of mine who did their PhD with Dorte, and we have similar in the States. And we also we've drilled 20 deep ice cores in Antarctica. So how many more do you need? I think our science questions in ice core science need to become much more targeted because we're not just drilling ice cores to see what it's like to drill through ice sheets anymore, right? We did that in 1968 in Antarctica with the first deep ice core at Byrd Station. Um, so I would argue my project is one of these. It might seem odd to work so hard for just 100 years of climate information, but if you're getting 100 years of climate information in a really critical place with 0 years of climate information, it certainly feels worth the effort. Satisfied with having the cores, and I wish I had had the same amount of time we put into collecting these cores. I should have been putting into building up a lab and analytical capabilities and all of this. But thankfully, we already have folks who specialize in the analysis of ice cores. I'm a little bit more on the new ice core collection side of the arc of what we do with ice cores. But then also, I'm really excited once we analyze these cores to then be back in the thick of trying to interpret the chemical signals and publish as soon as we can what they tell us about, year to year forcing of a place like the Thwaites Glacier or the Amundsen Sea. Can we put numbers on how anomalous temperatures were in any particular decade? Can we put numbers on how much the wind might have strengthened over that time? And constrained by observations. Right now, people are publishing papers on 20th century wind change from climate reanalysis model in Antarctica, which anybody who knows how those products are put together and how they're not constrained by observations would never be comfortable saying there's a 100-year trend in westerly winds in West Antarctica because only maybe the last 40 years where you have satellite observations, you have any constraint on whether that climate model that's producing those data is really tied to reality. So these ice cores are going to tie us into reality in the Thwaites Amundsen Sea region for the first time. So yeah, really excited to see what they can reveal, and that's what we'll be working on for the next year or two. Hopefully, always in the back of our minds of the next opportunity to collect more cores.
Oh, thank you, Peter, and thank you to our audience who have joined us today. This was a great talk and a great Q&A session. So yeah, I would like to thank everyone again for joining us today, and you can join us next Tuesday, September 23rd, by for a talk by Lazaro Vinola from the Florida Museum of Natural History, USA. And they'll be talking to us about paleoecology and vertebrate paleontology. Next up is tea time, where we can have extended conversations on everything ice cores, or how to accomplish your grad project dream. So I would request everyone just like take 2 minutes break, and we'll be back.